Good morning and good evening, and for Ansley, good night. We are going to start up in about 2 minutes. So just giving you a 2-minute warning, and then we will start the broadcast. Thanks. Okay, one more minute and we're going to start up. You ready, Scott?
I am.
Yes. Excellent. Okay, well, good morning, good afternoon, and good evening, everyone. I know we have people from all over the world. I don't know why Ansley probably is having trouble sleeping if it's midnight in Singapore and I can see him on here. So hopefully this will help you, or maybe not. Uh, my name is Christina Baxter. We are going to talk today about decontamination and the importance of having a decon and detection intertwined, because you really can't do one without the other. And so I own a company called Emergency Response Tips. I work very closely with ProEngine and Scott's team. So I will turn it over to Scott to introduce himself, and then we'll get going.
Yes, hi, my name is Scott Hartley. Welcome everyone here. The real reason for having these webinars is just to help increase some of the knowledge base out there about different problems that we see or different challenges that we see in the marketplace. So these are meant to be educational. They're also meant for you guys to ask questions. So hopefully we'll do a good enough job that explains a lot, but at the end, we will have a list for questions, and we definitely welcome the opportunity for you to ask some of those. We actually have a lot of videos in this one too, to walk you through, to show you things in real life with different scenarios.
Excellent. Now, also just remind everybody, like all the webinars that we do together, we are recording this webinar and we will make it available to you within the next couple of days, usually, to make sure if you want to go back through anything, you are more than welcome to do that. I see somebody is having trouble hearing. Can somebody else, Chris Weber, Ben, somebody tell us on questions whether you can hear all of us? Scott, you can hear me, correct?
Yes, I can hear you.
Okay, so it might be a sound on your computer. Kevin Johnson says he can hear us, so okay. So we're gonna start out, and if anybody else is having sound problems, we can bring it up later where you can go back through. So with that, I'm going to start and then I will turn it over to Scott partway through and then I'll come back to you at the end. So we're going to turn our cameras off so we can focus on the data and not these scary faces. So uh, with that, I'm going to turn off the camera. Okay, so as discussed, this is the Detect, Decon, and Verify project. And what we're trying to do here is to make sure that we're all on the same page in terms of the decontamination process, but also ensure that people go through and make sure that they can actually detect to determine whether they even needed to decon. Was there a contamination event? So starting off, what is the definition of decontamination? And this is where a lot of confusion comes in. Where we're talking about decontamination from an emergency response perspective, it's about reducing the total amount and preventing the spread of those contaminants. Very rarely are we able to remove everything. And a lot of that is because we don't know if we removed it all. And we'll show you a couple of examples where it looks to the eye like we've removed it all, but in reality is we may have spread it into a thinner film and may not have removed it. And so that's kind of what we're going to work on. So first off, what is our mission when we're going downrange to do decon? So primary mission, reduce the contamination levels. It's really trying to prevent the spread of the contaminants and prevent the possible exposures. And so if we can remove those down to the lowest level possible, that allows us to minimize exposure to the humans, minimize problems in the environment, and also minimize contamination on all of our equipment and other things. Now, for those of you like Kevin and others, secondary exposure, reasons behind this is to gather information. Oftentimes, those first few people, and we'll call them victims or casualties here, coming into the decon line might be able to provide you more information about what was happening when they received that exposure. So they're a great source of information or intelligence when you are starting your decon mission. Now, with that said, there's two types of decon we're going to focus on. The first, and the one that most of us are intimately familiar with, is the emergency decontamination. That can be either for individuals or responders, or it can be for mass numbers of people. And that mass number is going to change depending upon what agency you're with and what resources you have available. We also talk about technical decon, and that's a more methodical process. And that can be everybody from victims to responders to equipment. But what I'm going to spend most of the time talking about is this emergency decon, where we're immediately reducing contamination as quickly as possible. And in many cases, we will not have established a formal decon process yet. We also have to remember that decontamination and cleaning are two very different things. In decontamination, we're trying to reduce the amount as low as achievable, whereas anybody who had to be deconned should really be sent for proper showering and cleaning themselves afterwards. And so I want to make sure we're all on the same page here that decon and cleaning are not the same thing. Even if I decontaminate equipment on scene, I should still be doing an inspection and further cleaning if necessary when I'm back at the station for my equipment. So the first topic, time. If we don't start the decontamination process as quickly following the contamination event as possible, we remove that chance for getting as much off. So speed is extremely important. The time that the contaminant sits in contact with the material of interest, whether that be somebody's skin, PPE, or equipment materials, that time that's there allows it to integrate further into that other material. So there are many times where taking the time to set up a proper decontamination process is not suitable if you have somebody that you can see that has been exposed to a chemical. So the effectiveness you can see here with one of Rob Chilcott's demonstrations is as time goes on, your effectiveness for the removal of that contaminant goes down pretty drastically. And that's going to be really important here. The amount of contamination is also another issue to consider. So if we have a higher level, that increases permeation. So when you start thinking about a higher concentration of something on the outside of a surface going to the inside of a surface, the higher amount that's there will actually produce more going through. Sometimes if we can remove it down to a trace level, that trace level is not enough to even start that permeation process. And so that's where we're trying to do, is get down to that amount where, whether it's going to be permeation or penetration through something by the chemical, we're not going to be as worried because we've reduced the total amount. Regardless of whether it changes the permeation or penetration behavior of the chemical, it will minimize the total amount that becomes a medical countermeasure to deal with later on the individual that gets contaminated. Now, one of the things that's most important for us to think about in an emergency decon perspective is, most of the time, not always, we've always get those interesting cases, but most people who are involved in a contamination event are wearing some type of clothing. Doesn't necessarily mean that they're wearing protective clothing, but it could just be their regular work gear. It could be somebody at home who is wearing jeans and a t-shirt. But we know, based upon studies that have been done over the years, that most of our materials that we wear actually start to retain some of the gases or vapors. And we'll show you in some videos later this happening. But the reality is, if we can remove that outermost layer of the garments, we can get up to 90% of the contamination that's there removed. So just doing that first step gets us well on the way to our emergency decon objectives. Now, we may follow that up with something like enhanced ventilation if it's just a gas. We may use washing down with a fire hose if it is something that is water-based. If we use a higher flow of water, we might be able to use something for oil-based to remove it. And then there's always those emergency showers where we may add soap into the mix. But all of that's going to depend upon the chemical involved in the surface that it's on. But the most important thing to remember is 90% of the chemical can be removed just by removing the outer garments, by what deposited there. Now, another thing to keep in mind is the area on the body where the chemical is interacting. So if we are talking about a human, we need to prioritize the face, the neck, and the groin area, because those are the areas of the body where permeation through the skin is the fastest. And that all comes down to higher blood flow areas, areas where we have thinner skin materials, and areas where we might have higher humidity or moisture. And as you can think about with anything with permeation, increased humidity, increased temperature, and decreased thickness of the material all play a huge role in the chemical getting through. This is why, for all of you that are firefighters, we are so intent on you getting that soot and material off of your face and out of the scrotal areas as quickly as possible, because those are the areas where permeation is going to make a huge difference. Now, with that said, there's a couple of principles that I like to set all of my decon by. So first, we have to decon as soon as possible. We cannot let that contamination sit on a surface until it becomes part of the matrix. So it doesn't matter whether that's skin, equipment, different types of materials will start to pull that contamination in. So we need to remove the contaminant prior to its making its way there. We need to decontaminate only what is necessary. So for instance, if somebody had a splash on their leg, why are we wetting down the whole body? Or to make it even more interesting, if they had an upper body contamination but not the lower body, if we are running water on them, are we not increasing the surface area of the contamination by moving it along? If we can, it's best to focus on the area where the contamination occurred and not spread it further. So minimize your resources, minimize your waste, and minimize the total surface area of the contamination. Decon by priority, that's going to be situation dependent. A lot of that might be somebody who is exhibiting medical symptoms and we need to get them out of there and start working those medical priorities. It could be responders that we're dealing with, and somebody could be low on air or having another medical emergency. And then with equipment, we're going to look at the different types of materials that equipment's made of. I might wait on something that's a steel based, whereas something with a rubber sleeve, I'm going to try to get that deconned as quickly as possible because it's got a much more chance of the chemical getting in. We also want to decontaminate as far forward as possible, and that's just to limit the spread of the contamination. And so let's think about that for a minute. As we start building more vertically in our environments, and let's say there's a drug lab and it's on the 10th floor of a high rise, do I want to wait until we get the people all the way out of the building before I start that first level of decon? Or do I want to try to get them decontaminated as they come out of the contaminated space? The issue we have is if we bring them all the way out, we likely have increased the area of contamination and greatly increased the potential for secondary contamination. So what we would want to do is minimize as much just outside of the area of contamination as possible. And then if we need to do a more detailed decon outside, that's perfectly fine. But bring it back to the area of contamination and try to minimize that spread. So this is kind of the cheat sheet that we use, and this is one we use for our Hazard 3 classes. And it's, if you have emergency decon, we're talking to you now about the fact that time really matters. And so oftentimes that first due unit is the person who's going to have to initiate decontamination. Because if we wait for decon until we get the hazmat team there, in most scenarios, the hazmat team is a secondary response asset, meaning that the time between the first responder getting there, which may be between less than 5 minutes, to the second responder get there, which might be up to 10 to 15 minutes, there's a lot of time where that chemical can become embedded into the matrix of what we're worried about. And in this case, it's the human body. So that first due unit is the person or people who are going to be responsible for starting this emergency decon process. With that, most of them won't have advanced detection equipment with them. So in this case, the victim becomes the first detector. So that human who is exhibiting signs or symptoms of exposure is the person that we're going to use. So with this matrix on the left-hand column, I have signs and symptoms. And across the top row, I have the state of matter. Is it a gas or a vapor? Is it a liquid or is it a solid? And so what you do is go forward and say, from the first arriving unit, do I see what appears to be a gas or a vapor? A liquid, is their clothing wet? A solid, are there particles all over them? And then I come down and say, do they have any symptoms? Do they appear to have a cold or allergies? Or am I looking at them and thinking, call an ambulance? Okay, so those are my 3 levels of symptomology. 1, nothing, I can't tell whether they've been affected or not. 2, I can't tell whether they've been affected or if they have allergies. And 3, no matter what, I would transport this person to get medical care. Now I come across and I look at where it puts us. If we had a gas or a vapor and that person has no symptoms or minor symptoms, our best bet at the emergency decon level is just remove them to fresh air. So if we can enhance it with a fan, even better. Gas onto the materials, gas comes back off the materials. We have done several studies of this with human skin and with freshly excised human skin, as well as different clothing materials, and find that if it's a gas or a vapor, they very rarely hold in the chemicals of interest unless that clothing is wet. Now, the next level would be a liquid. You're seeing material on their clothing, and they're either having symptoms or just minor, no symptoms or minor. In this case, we're going to remove that outer layer of clothing. We don't have to take away everything, but if they're wearing denim or heavy materials, go ahead and get that removed. Try to ensure their privacy as much as possible, but these people that are in the yellow, just like the people in the green, are able to take care of themselves with you providing guidance. Until you hit red, you should not be the one doing the work. You're providing the guidance and allowing the people to help them with your expertise. Now, when we get to those solid materials where you have particulates that may be all over the clothing, we may have to ask them to gently wet that before they remove that outer layer. If there is a material that is all over the front of a shirt per se, you may want to help them by cutting off their shirt instead of having them pull it over their head, because the last thing we want to do is increase exposure to that face, mouth, eyes region. Now, obviously you can see down in the red is anywhere where we have serious signs and symptoms. Now, if we just think about this for a moment, and we're talking about trouble breathing, burning or discoloring of the skin, degradation of clothing, the chemicals that we're talking about here tend to be strong oxidizers or strong corrosives. So when we start thinking about that, when we deal with decontaminating corrosives and oxidizers, we're generally using a high flow of water. And that's oftentimes the only time we use high flow water anymore. Now, if it's a gas, we may want to flush their eyes only, remove the outer clothing, and enhance ventilation with fans, because the gas is not going to stay into contact with their skin for long. Whereas as we get over to the liquid and solid, we want to blot any of that observable material as quickly as possible. Then we'll start flushing them. Because we don't have a lot of other assets here, we're going to start at the head and move down the body and try to continuously flush to minimize chemical pooling in any areas of the body. If you've practiced this before, it's very difficult to stop pooling if the patient is lying down. Remember, when the patient is on the ground, we'll get pooling behind the neck, in the ears, behind the hair. We'll get pooling at the buttocks and other areas like that. So we need to, if we have a patient who is not mobile, we need to be very careful to ensure that we do not increase injury by letting materials pool in those areas. After the initial flush, you want to get that outer layer of clothing off. The only reason we have you do an initial flush first is because sometimes the material is already adhered to the skin by the time you get there. We want to get that off of there, but knowing that if we initially flush, we are going to push some material through to the skin. And then, of course, once that outer layer is removed, continue flushing until the specialists get there. In any of these cases where the red is required, you need to flush for a minimum of 15 minutes. And that's just because we know that corrosives will continue to interact with the skin for a minimum of 15 minutes with free-flowing water. And it's shocking when you start thinking about the amount of free-flowing water you need. If we just look at it from 1 milliliter of a liquid, so we're now in the suspected contamination as a liquid material, so middle column in bottom row. And we're looking at that and saying, this liquid has gotten on somebody. If I just use flushing and don't do any blotting, and I had 1 mil only of a strong corrosive, if I was just doing dilution and looking at the pH scale, it would require me to use 1,000 liters to actually dilute 1 milliliter of a strong corrosive. That's 250 gallons of water per milliliter. This is why blotting with an absorbent material becomes so important, because if we can blot up as much as possible, now we've greatly reduced the amount of water we need. Now, that's just using the dilution process, knowing that having a high enough flow rate of the water will also help us with physical removal, and we'll get into that a little bit more. But this table is meant to be with the first due units, and it's identify whether it's a gas, a liquid, or a solid, and then no symptoms. They might have colds or allergies, or serious signs and symptoms. We're transporting them no matter what. So we talked about blotting. This becomes something very important here because we have a lot of people who don't understand the difference between blotting and wiping. If we are dealing with skin, we must blot. That means we are going to take the absorbent material and we are going to hold it against the skin. We're going to leave it there for up to 10 seconds and allow the absorbent to do its job. What we don't want to do is apply pressure and pull it across the skin, because what that does with the skin surface is it will actually push it in and provide friction, which will allow it to get in faster and more thoroughly into the skin surface. So we may wipe on something if it's an object. But when we're talking about human skin, we do not want to wipe across it until after we have blotted up as much residual material as possible. And at that point, we may be able to wipe. We also need to remember not to wipe on PPE if we're around interfaces or around zippers, because that wiping process may help push it through the interface or through the zipper. Blot there as well. Now, when you choose a dry absorbent, I know this is a crazy chart, but this was something that was done by Kassouf et al. In 2017. And they went through and looked at a bunch of different dry absorbents, whether they be things from the hospital or things from the commercial marketplace, and looked at them for both their water absorbency and their oil absorbency. These are two of the things that are critical considerations when you're choosing what type of dry absorbent you should use. So when we're talking about those absorbents, we need to look at the water absorbency, the oil absorbency, particulate adhesion, how well will particulates hold to it without becoming a secondary contaminant, chemical compatibility, not a great thing if we put it on there and it starts to burn, secondary contamination potential, does it go into the material or does it stay on the surface? And then, of course, all of us know that while we don't generally talk about cost, cost is one of the biggest driving factors. And then also availability. Now, when I look at these, some of the things that work the best. So what we're looking for, the things in the top right, and that's got great water absorbency and great oil absorbency in the same product. Now, there are going to be times where we may have to go, and I teach this one all the time, where we use the white balls, and the white balls that are oil absorbent are the blue ones, and the white balls that are water absorbent are the white ones. And you keep both around and you just figure out which one you need. They work pretty well, but they're down here a little bit above these kitchen towels. So they'd be up in the middle here. Now, what I'm trying to find is one product that works for it all. The one that, from a DoD perspective, when we were doing research, was coming up with the FiberTech product with Texas Tech University that was then licensed by First Line Technology. But this FiberTech has a cotton material that helps us with the absorbency, but it also has a carbon in the middle to help with the adsorbency of the different gases and vapors. So when we start looking at it and say compare its water absorbency and its oil absorbency, it's really about what's going to give us our best bet in one product. Now, obviously, some of these incontinence pads and the ambulance underpads work fantastically as well. Most of your wound care dressings are going to come up in here. They just tend to be very expensive as something we can use, but we can use them pretty quickly. Ansley Fuller's Earth is one of the ones that we tested. And in fact, the Fuller's Earth, we started using that for defense in the 1930s. In reality, Fuller's Earth is a fantastic absorbent material, but we stopped using it because it wasn't bound into something. Now, when we developed the FiberTech, Fuller's Earth was one of the 30 adsorbents that we looked at, and it did not do as well as when we had the carbon that's included in that FiberTech. And that was actually done in 2003 under a defense project. So just looking at this, balancing what you're looking for. And then we actually did this one. This actually was in 2023 and was done by ERDIC at Department of Defense. And what we were looking for here was a cold weather decon, but looking for a dry type of product that we could use that would replace the HEPA-Vax, which, just like when we're talking about detection, we always talk about GCMS as the golden rule. HEPA-Vac is the golden rule for particulate removal. But in this case, we're looking at other commercial products to say, can we get that level of performance without having to try to vacuum somebody? And with this, the product that came out that matched the HEPA was the first line. Now, the first line did not do as well at the ultra low temperatures as it did at the moderate to high temperatures. The other one that it didn't do well with is in a cold environment, you had to wet it if you wanted it to minimize secondary contamination. So what was happening is in a cold environment, the particulates were staying on the outermost layer where it was a quilted fabric, and so you still had it available for secondary contamination. If you wetted it, it actually pulled them inside. Very cool study. The other one that did pretty well was the M2 Decon multi-purpose Decon wipes. Not quite as well as what you get with a HEPA-Vac or with first line, but it did pretty well. The one that did not show up well was the Christianini SX34. The problem with that one in many ways was not the product, but in many ways it was the test method. So a lot of this, because it leaves a residue on the surface, it made it very difficult to tell what was residue from the product and what was residue from the actual threat material. So really an interesting study. So you can find that online. It was the ERDIC TR23-3. So that was last year that they released that. Now, this is what we use with the FiberTech. That's a 3-layer non-woven. What you see on the outermost areas is an absorbent material that is cotton-based, but it's a fabric that is quilted on there to get increased surface area. You also see sandwiched in the middle an activated carbon core. And we did a bunch of studies in the early 2000s against 30 different absorbent materials. And what we were looking for was what removed sulfur mustard the best, what removed parathion the best in terms of using that instead of VX, and then what did water and standard oil-based materials. So we were looking for hydrophobic, hydrophilic, and then we also wanted to make sure it didn't degrade with some of the things we used. So in this case, we studied 70% nitric, 70% sulfuric, 10% hypochlorite solution, which was because that's what we were using for Decon then, and then paraxylene for an organic. And then we also did the sulfur mustard, the methylparathion, and while it outperformed most things, it did not outperform everything in every situation. Okay, so for water absorbency per se, there were some others that did better at water absorbency, but they didn't do well for some of the other chemicals. And so in a balanced approach of the 30 materials, this was the final product that was pushed forth. And it became called the Personal Decon Kit. Now, the other one we have to think about is when it's mass contamination and we're thinking about free-flowing water. In this case, the water flow rate and pressure play a really important role. You can see some of the work done by Chilcott in 2016, which showed that it's actually a 2 gallons per minute flow rate there that was the most effective. And you didn't really get any more effectiveness after going over 2 gallons per minute. But what we had here also is work that Brock did when they were trying to come up with low flow showers and figuring out what was the optimum flow rate and pressure that would allow water to be used for a physical removal process. And this is where emergency shower standards come into play. So an emergency shower or a low flow shower for a home are designed to give you the flow rate and pressure that will allow for physical removal instead of just dilution. In this case, if you're designing a system, I would go with something that was 2 gallons per minute and something around that 45 PSI. That will allow you to get the physical removal, but also you're still going to take the advantage of the dilution effects. So you're not going to have that 1 mil goes to 1,000 liters or 250 gallons. You're going to have it much faster. Still going to take you about 15 minutes of flow. Now, when we get to the technical decon, in this case, I like to go through and either, if we know the specific chemical, we can go into our emergency response decision support system the ERDSS. If you don't have that, it's chemicalcompanion.org. To register, you must be a first responder or military personnel to access it. But in that case, you can look up each chemical and it'll give you details on how to appropriately decontaminate. But in this case, we're just looking at classes of chemicals. And as we started to cluster materials together in the guidance from all of our scientific studies, we found that fan-based decon, just enhancing ventilation, works sufficiently for toxic and corrosive gases at less than lethal levels. So we did not start to get interaction with the skin for most of these toxic and corrosive gases until we were above lethal inhalation levels. So if we're talking about a victim, not a cadaver, then we're generally talking about a fan. When we got to our materials that were explosive or flammable gases, flammable solids, any of those flammable materials, a dry-based decon worked best. Same for radioactive. And in that case, we're talking about using a dry absorbent. When it got to oxidizers, organic peroxides, and corrosives, using water worked the best. And pretty much the others all ended up going down a blot, apply, remove, or a hybrid type approach. And what we were doing there was using a blot to remove the highest amount possible. And then we may apply something if you have something like RSDL, if you're doing skin, or another material, and then remove that. And that was our hybrid decon. That worked wonderfully for chemical warfare agents, some of the drugs, poisons, and then you always are going to have your specialty things like mercury, where you need to bind it with sulfur or something of that nature. As we go down these, it's just trying to give you a little bit more information, but obviously for the wet, if we can blot first, fantastic. If we can't, start flushing. For the dry, you can do everything from blotting and using absorbent materials. You could brush some of these and you can vacuum them. For the fans, putting in fresh air will work, but you can also put PPV fans on them and really increase that level. Bio, it's going to depend upon what it is. And frankly, for biological, you really need to go to the EPA certifications and approval process and make sure that it's approved for that type of material and understand what the contact time is and what the pot life is. Those do not apply to bio on the skin. They only apply to bio on a surface. And then the hybrid decon, obviously, when we start going down these things, we want to be really careful, but we want to blot as much as possible so we don't increase surface area and we don't increase penetration. So the way I look at the hybrid decon is really first, did a chemical exposure occur? Sometimes we can visually see that. Many times we have to detect it. If it did occur, is it interacting with the skin? And if so, usually you're going to see irritation. We can talk about redness. We can talk about dermatitis. And all of those things become an issue. If you see anything like that, and it may be on one individual and not all, because somebody may have a specific allergic reaction, blot as much as possible. Hold that absorbent right there against the skin and let it do its job. It will naturally move to the material of higher absorbency. The skin is a fantastic barrier material. So you want to do that as much as possible. Then we may apply water, soap and water, or appropriate decontaminant. Just remember, in this case, if we're talking about skin, and if a material is not water soluble, we may want to minimize the use of soap so we don't increase its solubility in the skin. What we want to do first is try to get as much off as possible, knowing that we may have to use soap and water to get that last bit off. And then, of course, remove any residual soap or decontaminant so you don't end up with a secondary irritation. Now, if they had no interaction, we're just going to increase ventilation if they're coughing and wheezing. Otherwise, we may just have them stand to the side and monitor them. Another question that I just saw is, can we vacuum liquids? And that's going to depend upon what liquid and what vacuum. There are certain vacuums that are for vacuuming liquids, but in most cases, the liquids on a person are going to get into the materials, making it hard to vacuum. If it's on a surface, absolutely. We use a vacuum oftentimes for liquids for collecting samples. Now, when we get to the technical decons, where we have to start thinking about the environment as well. If it's an emergency decon and we're talking about a human that has something on their skin, we're going to perform our actions as quickly and as efficiently as possible, regardless of the situations we are in. We will then deal with hypothermia problems and issues like that. But environmental conditions can become an issue when we start thinking about those longer term decontamination processes and things of that nature. So this is out of the SBCCOM report from 2002, where they came up with temperatures that were most likely to cause a hypothermic reaction if you were in that condition for a length of time. So anytime you're greater than 65 degrees, you could do everything outdoors, decon, follow-up, whatever you need to do. If you're between 35 and 65, then you should try to cover and shelter them, but follow up indoors. And then, of course, if you're less than 35, you need to have some type of heated shelter decon corridor and then follow up indoors. That indoors may be as simple as bringing over a bus or something of that nature that's heated. What we're trying to do is not leave the person in cold with wet body and try to increase their chances of hypothermia. Now, sometimes you move patients. If you're moving a patient who is contaminated still, we've got to think about what that material is and what its vapor pressure is. If the vapor pressure is high, it becomes a problem with the contamination removal. If we're talking about bringing them indoors into a confined space following decon, we need to ensure that the decon was sufficient to ensure that there's not going to be a problem with off-gassing in that space. So that's where we have to start thinking about our decontamination being intimately tied to detection. First off, we should always use detection to even determine whether they were contaminated. So I'm going to turn it over to Scott for a few minutes and let him go through some of these topics, and then I'll come back at the end. So Scott, over to you.
Thanks, Christina. So what we're going to talk here is one of the most important aspects of the challenge that we're dealing with decontamination systems and detection systems. Is a lot of times people buy detectors and you buy decon solutions, but a lot of times they aren't taught how to work together with those in tandem because there are some nuances associated with them, and then we're going to talk through those. The fundamental point that you start on the detection side is determining what level of detection, what level of material is present and where it is present, and if it is present is the other important thing on there. So do you have to go through a decontamination cycle? In the case of the detection, you kind of have two scenarios. So one is you already know what you're dealing with, so then you're just looking for that. The second is I may not even know what's on there, and then I have to go through and determine that. So we'll talk a little bit about that in the next slide. But on the detection side, especially from a concentration standpoint, what you need from a detection standpoint is something that's very fast responding and continuously responding in order to get you that feedback quickly. You don't have the time to take individual samples and put them on there. Or if you need to do that in the case that you don't know exactly what it is, you need to actually know exactly where the contamination location is so you can get a good sample. So if you don't have a good sample, you don't get the good information that you really need outside of it. So the first part is understanding where it is, what level it's at, and understanding where I need to decon and where I may not need to. If it's a large structure, it's not physically possible to do all of it, right? So we have to know where it's located and where it's not, especially on the human. It's also important for us to understand because that'll impact the way that it can enter into the body based upon what it is and the nature of the risk that that person's seeing, and especially in a mass casualty decon standpoint, you're obviously having to prioritize people. So having that information on concentration and location becomes very important. So then you enter into the decontamination solution to get rid of the material or to reduce the material as much as possible. And then we need to do a verification process on there. So if you go through a decontamination, you don't actually remove the material that you need to, that kind of defeats the purpose, right? So we have to go through and understand what the decontamination, verify that we got in the locations that we aren't getting that. Now, it's important to note when you're doing just your basic detection to find what it is at, you're your detection in parts per million is okay for that. Your continuous detectors will be your IMS, your PIDs, your flame spectroscopy machines will let you do that. They'll be pretty fast at responding them. Obviously, you need to know what that material is. So you can have a PID and you could have hydrogen sulfide, for example, and those response times are much higher. So you need to be aware of what the response time is for your instrument when you're doing that, because the worst thing you can do is have a false sense of security where you're doing it and you're like, oh, this, I didn't get a hit. I was only there for 5 seconds, when reality it's 45 seconds for you to be able to see it. So you have to be cognizant of that. But it's really from the PPM part to the verification is you're really PPB, because one is you've taken a lot of that material, but two, in certain cases, especially on, and we'll talk a little bit more about this on your organophosphates, for example, your skin detection becomes very important, but then just the level of material that's needed to cause a problem or continuing to cause a problem for you is different based upon what the material is. And we're going to give you a couple examples where certain materials are going to get off really quickly. Other materials are going to stay there for long periods of time, and the decon is going to look different, as well as the verification process for both of those in there. So it's also understanding the materials and the temperature range that you're in as well, because that will contribute to the amount of material that's coming off. If we go to the next slide, one of the things that we talk about here in the nomenclature, just to kind of give you a baseline of that, is there is a difference between trace and bulk detection. So again, this is one area where maybe some of our choice of the words of bulk and trace may not really be helping us, but as a general rule, what we're defining trace as is our continuously sampling methods that allow us to identify things, versus a bulk detection where you actually have a bulk sample or a sample that you put into a machine that needs to come out. Now, sometimes people are saying, well, I can do trace detection, meaning I have traced very small amount of material, but you're still doing a bulk detection method. So it's important to define what the words actually mean associated with this. And maybe the use of the words trace and bulk is maybe not the best in this case, but it's important to understand what we're actually saying. We're saying trace. So trace is very sensitive, very fast responding, continuously sampling solutions. But in many cases, you can't 100% trust what they're telling you from the standpoint of, in the case of a PID, it's going to be cross-sensitive to a lot of things. So just because it's going off on one channel doesn't necessarily mean it's that specific material that it's causing it. You have to understand the cross-sensitivity of that. If you're doing it with an IMS instrument, there are false positives associated with some of those where similar materials have the same molecular weight. And so if you're putting those materials that have that same molecular weight, it'll say, for example, I'm hitting on a nerve agent, and it's not. It's a cleaning solution, for example, that could cause that. So just being aware of your detection technologies with them. In the case of your bulk detection technologies, those are things such as FGIR, Raman, high pressure mass spec. So those are where you're primarily doing some sort of scanning of the material, and it's giving you a result. In many cases, there's spectrum that are produced from that, and that spectrum allow us to identify those materials much more high confidence level than you will get with your other trace detection methods associated with those. So the two work together, but in the case of what we're talking specifically on decon, it's sensitivity, response time, or what are your key attributes that you're really looking for and really need for those sort of applications, especially once you know exactly what you're dealing with. Go to the next slide, please. So when we're actually dealing with the person, it's important to understand a couple things. So once a person has gone through either emergency or technical decon, we obviously want to monitor or validate that decon's done properly. Why? Well, in the case of there's emergency decon, we need to get them to some sort of more advanced treatment. You obviously don't want to be bringing a person into a hospital that's off-gassing that now can affect the first responders, the doctors and the nurses that are doing that. So we have to do some level of verification that, yes, this person's good, they can go forward with that. Now, when we're doing that, we need to monitor. Again, we need very sensitive instruments, so down to the parts per billion associated with that. So in those cases, your two instruments that are going to get you down to that high level very fast are your PIDs and your flame spectroscopy machine or the AP4C. IMS is not really great for that. It's because it just can't get down to the sensitivity, nor does it have very good response time at those really low concentrations. If you're outside in a controlled environment, if you're outside and there's wind associated with that, it's very important to do two things. One is the person, whoever's doing the detection onto the victim. So the first responder needs to be standing upwind. The reason being is that downwind will be, where the materials will be pushed towards. There'll be higher concentration, there'll be more atoms for us to see associated with that. Obviously, you don't want to be standing where you're getting contaminated as well, potentially. You're trying to maintain, if you go down, that does not help the situation. So stand upwind, sample downwind. Stand the detector as close as possible to the surface. We say around a ½ inch. Obviously, do not touch. The reason being is you can cross-contaminate, where your detector is going to continue to go off because you actually put some of that material onto the detector, and it's going to continue to sample that associated with there. You start with the hands, move up and down, as well as the legs. Kind of your extremities are kind of your best places for you to do that, as well as if you remember the previous step is if you know exactly where those people were contaminated, and a lot of times the person itself can tell you, then you obviously want to concentrate on those areas where the exposure occurred. Now, a lot of things that we deal with are heavier than air. They'll be down towards the feet area, most likely, or people like to put our hands in things that we shouldn't. And so therefore, those are why those extremities become those important places for us to try and sample to verify that we've done a good job of decontamination and we're near where we need to be. And then when we have that, we can kind of go to the next slide, which is just kind of a quick overview of how flame spectroscopy works. For those of you who aren't aware, why does this work for a good application for decontamination? So in this case, it is a continuously sampling process. So there's a fan that pulls air constantly through the detector. So what we're seeing here is the upfront part of the detector, which is a pre-burner. Because we do have a flame in the material, it helps keep that flame from propagating outside of there. So the materials are coming in. Notice there is no filter of the air coming through there, so that becomes important in the case we're dealing with aerosol threats associated with that. Aerosols can be a little bit more difficult to do. So what you have here is a flame. What is the purpose of the flame is just to add energy into the airstream, and what that does is that excites the atoms, moves them away from their ground state to an excited state. When they go back into their ground state, certain elements produce an emission, that emission specific to that element and to that element only. So what we have is a series of lenses, and we have a sensor that's able to capture all that spectral information. And so what we're doing is we're looking for the fingerprint of certain elements of interest that are key for a lot of toxic chemicals as well as chemical warfare agents. So that's phosphorus, arsenic, hydrogen, nitrogen bonds, sulfur. Those are all kind of base building blocks of your CWAs, or as well as a number of ticks and TIMs. And so it's really an elemental detector that you're doing. But because of the fact that you're using light, it's an extreme and it's a continuous process. You're able to see down to very low concentrations, as low as 1 microgram per meter in the single parts per billion range on the organophosphates, for example. So that's why it's a good tool to be utilized, and why it is a good application for decon in particular, because of the fact that you're wanting to get data at very low sensitivities and very quickly. And that's why it's super helpful in that sort of application area with there. So what we're going to do now is go into a series of different scenarios that you'll see as far as decontamination, and then we'll kind of give some help on how to do there. So the first one, and you could start the video with that, is, so we're doing ammonium. So ammonium, as you know, has a very, its vapor pressure is less, vapor density is less than air. So therefore it'll evaporate off fairly quickly. So what we're seeing here is turnout gear. We have some ammonia in there. So if I put the detector over there, boom, it's gonna hit real fast. You see it gets it does a quick response in there. But even though you have this turnout gear, it is permeable. And what we're seeing here is the fact that it is permeating through the turnout gear. And what that actually means is it'll be inside the turnout gear as well. The good thing is, because we have a vapor density of less than 1, it is lighter than air. So air or pushing air through the system is helpful for us. So that's why fans are very good for that, associated with it. So you can kind of see here what we did is we exposed it. It was going through the material. We removed the material, and that, as you can see here, you're using the AP4C to verify that you now are clear and you no longer are off gassing associated with that. And then in case, the big thing is if you still have that material there, fan it out as quickly as possible. You're taking advantage of the fact that the vapor density is, and that helps solve that problem or helps decon that situation. The next slide will be something now that has a higher vapor pressure than one, so it's heavier than air, and that's we're dealing with sulfur dioxide. So in this case, we're creating a mixture of that. You can do a couple different ways, but you're seeing that we're mixing acid gas, and then we're putting a piece of turnout gear on top of there. We're letting it sit for about 2 minutes, so that material didn't go through, but what we're seeing here is on the bottom side of it, it's present. Again, the same thing will apply. We want to just use air and to off gas that material. And so what you're going to see is that it does take longer because of the vapor density in this case. So it's following the science of what you would expect. But in this case as well, similar to the ammonium, by applying a fan to the surface of the material, you'll be able to drive off those atoms in the material quicker, but it will naturally just occur with it. And you're kind of seeing here a slow degradation over time as it gets lower and lower. And then when that goes away, then you know that person has been cleared and that can go out of the situation. But again, also to what Christina had talked about earlier, a lot of this will be in your clothing. So therefore, removal of clothing in certain cases will be helpful and remove a lot of that material automatically, but it will go through, as you're seeing, in some cases it goes through it can go through your skin. So you obviously need to treat that, especially if it's either a acidic or a basic response on it too. But again, fans in these cases will help you, primarily driven by the nature of the material. If you want to go to the next slide with it. So another common scenario, unfortunately, that we're seeing here is drugs. In the case, we're doing a mixture of fentanyl, so that white powder is fentanyl. So what you're seeing here is a thermal heater that we use, which is also helpful in certain decon applications. So we took a sample of that, and what we're doing is we're adding heat to a powder. So in this case, what you're doing by adding heat is you're increasing the vapor pressure of those materials, allowing more of the atoms to be released and then be able to detect it. So fentanyl has hydrogen-nitrogen bonds on it, so that's why the hydrogen-nitrogen bond occurred on the material. So you're seeing what your normal process would be in decon. First, you want to get all that material off the surface. Now, even though that material looked pretty clear, we don't see any white powder on there, I'm taking a sample of it, and I'm going to introduce that into the detector. Again, on the second set of bars on there is your hydrogen-nitrogen bond where it's going to hit. So we're adding the heat again, and we're going to see if we still have materials present. And the answer is yes. So that's one important, is even though your eyes tell us, hey, it's deconned, there's still materials that's present. So if we needed to, because we can't guarantee that we can get all those off, we can now apply a hybrid decon process. In this case, we're applying Dahlgren decon to the surface of the material. So first it's mixed up, and then you're applying it to the surface of it. You're waiting the 5 minutes in order for it to do its thing. And we're almost there, thumbs up. And so now we're gonna take that material and wipe it off and allow it to, basically now we have done a topical decon of the solution associated with it. So one of the things to consider that sometimes people don't necessarily think about is, so I have removed that material. In many cases, what I do with the decon process is I make that chemical less harmful or break upon some of those bonds, but the elements are still present. So if I take a sample scraper again, go into that water, so those elements, those hydrogen nitrogen bonds that were present in the fentanyl are still going to be present in that solution. So some of those bonds have been broken, so therefore it's not as harmful to me. But decon does not magically make atoms go away. Those atoms are still present, and so we are able to still detect those in the solutions as we should be able to. So again, it's following the science, but I think sometimes people think that decon is this magical solution that makes things go away. It really doesn't. All we're doing is we're trying to make it less harmful and break out some of those harmful bonds that really make those bad. So in the case of most of the things that AP4C will detect, you want to get rid of them. Just be cognizant if you're dealing with things that have arsenic in it. So you're breaking down, you still have arsine present in those solutions. You need to be still careful associated with that. So if you're dealing with lewisite, yes, I've broken down the lewisite, but you still have arsenine and other materials that are pretty harmful in there. So that solution is something you want to make sure you properly dispose of carefully, because they still have some harmful materials present. Some of those atoms that we have still are pretty nasty by themselves with it. So go to the next thing. So now we're going to do malathion. So malathion is a good simulant. It's an organophosphate, so it's a good simulant for organophosphates, so your nerve agents associated with it. Now, most nerve agents, most malathions, most nerve agents are really insecticides and pesticides. I like to call them humancides. They're just designed to be effective against humans. And so they tend to have very low vapor pressure. They tend to be oily substances that like to stick to surfaces. Like, you don't want to apply an insecticide and the first time it rains, it goes away. So these have very low vapor pressures in comparison to what you're seeing. But if you hold the detector over them for extended periods of time, you should be able to detect it. Even your Novichucks, which have extremely low vapor pressures, much lower than what we're talking about here, we can still detect with AP4C in open environments. So what we want to do, again, following that same process that Christina talked about, we want to try to get as much of that material off the surface. So what we're doing is blotting and then trying to carefully remove that. Now you can still kind of see there is some light diffraction that's occurring on the surface. So you can kind of see the fact that there's still some material in there. We're wiping that off. So we probably have removed probably 99% of that material in there. You can actually, with low vapor pressure materials, you can actually potentially even get a higher hit on the detector once you've removed a large amount of that material on there. The reason being is you've increased the surface area of which that material has been placed on the material, and it'll tend to off gas a little bit more, and you'll be able to see that a little bit more. So even though, again, I've removed a high percentage of that material, probably in excess of 99.9%, it's still present on there. So again, especially if you're dealing with some sort of nasty chemical warfare agent, or you still want to go through the decontamination process, the topical decon. So we're following that similar process with the Dahlgren, applying it onto the surface of the material, allowing it to sit, do its thing. Now, when it's applied on here, unless it's been recently mixed, like just fairly new, there is some parasitic acid in the Dahlgren solution, so you could pick that up when it's freshly made. As it's sat there for a couple minutes, you aren't going to do that. Since I applied it to the surface and I'm really covering a lot of those atoms that are no longer able to off gas, we aren't able to detect anything. So if you're dealing with something like VX or other things like that, you would now have a much safer environment than you did once you've gone through that process associated with it. Now, this is just showing you that. So this is fresh Dahlgren Decon. And so we're just applying it onto that surface, and then we're going to pick up some of that parasitic acid into the solution. So why that's important. This is also the reason why we should be probably doing a better job as an industry of showing detection and decontamination together as a system, is the fact there are some nuances to each detection system and each decontamination solution. And so because there's parasitic acid, it's not bad that there's there. But if you're using that to say, hey, have I finished doing this or not, and you're getting a hit on phosphorus, it's important to know that you're going to get hit on phosphorus, especially during the initial mixing process. So not to be alarmed of that. Potentially, you can maybe even get some off gassing when it's first just being mixed, and that'll go away. It should be below detectable limits, but it is present in that solution. The next slide, if you want to go to that. So here is a fun experiment that we did. So even though I've removed, again, using malathion into the solution, so putting that down onto a surface, what I'm going to show you here is how we can use, if it's a really cold environment, for example, and we aren't getting a hit on much of anything. So again, this is malathion on there. So in some cases, I may not be getting a hit on that solution, what I can do is use headspace methods in order to increase the number of atoms that I can then see and associated with there. So I'm going to show you a cool little thing that we've recently developed that can be utilized to help do that. So you see here, this is a headspace collector associated with it. It's just a simple piece of paper. So what I'm doing is putting it over that and then covering the top of it. And then basically what is occurring inside of it is I'm increasing the vapor pressure of the material. You almost get up to a evaporation cycle similar into there. So by doing that, I'm allowing pressure to be built up, and I can put a detector. I'll move, in this case, I'm putting the AP4C plus. The AP4C and the AP4C plus have the same detection thresholds on there. So I'm putting that over there, and then you see, boom, I'm getting a hit a lot faster and at a higher concentration. That's simply by using headspace methods. Now, we always, as a general rule, want to try to use the number one thing is just putting the detector over, because that gives most operational information. But in the case where you don't have time, or you know that it's cold or other things like that, I can use headspace methods. So again, going through using FiberTech, applying it to the surface, trying to get up as much of that material as possible off of the material. And here we go, it's still working its thing. So wipe it off, and then we're going to try to sample again. So bring that system over there, and we're going to try to detect it. So remember, sometimes when you're blotting it, you don't want to swipe it or move it over large surface areas, because you can actually release and make that situation a little bit more harmful with it. Now, again, using the same headspace methods, again, going to build up a little bit of extra pressure and then try to detect it once again using the detector. And even though, again, we've removed a large percentage of material that was present on there, so probably from a weight standpoint, we probably removed like 99% of the material that's there, there's still a number of atoms that are present. We're still able to detect. In some cases, you shouldn't be surprised, even though you've taken a majority of the material off, that you actually can have a higher concentration once you've done that, because you've turned something that was primarily in a liquid material and you made it a little bit easier to aerosolize and going from there. So even though a lot of times things look like they're off, there still is material on there. And that's also important. For example, if this was skin, the same thing could happen associated with it. So again, I'm going to bring it over the AP4C over it, and we're going to see if we can get a hit. So this would be validation of post-decon. So in this case, there still is off-gassing that's occurring, and you will tend to see higher off-gassing potential with organophosphates than you will with some of the other materials, which are going to blow off very quickly onto that surface of that, and that becomes important. So in the case of the Salisbury Novichok incident, that material got absorbed into the skin. They were still able to continue to get that material out of the skin a number of days later after the exposure. So those things are just nasty and they will come out. So what we're trying to do is minimize the amount that gets on the skin and the time that it's able to sit on the skin. The quicker we can get that off the surface, the better off we're going to be. But when it's in the skin, it will still off gas. And so it's important to understand that, as well as the risk associated with it. That's why having these very fast detection methods and very sensitive down to 1 microgram per meter, just down to single parts per billion, becomes very important from a detection standpoint. If you want to go to the next slide. So I just want to talk to you as far as response time of chemicals. So what you see here is a release point. So inside that glass tube is controlled amount release of ammonium. And so we have 3 enter points that we're able to introduce that. So what we're able to do is we have multiple detectors sitting there. So we have IMS, PID, FTIR, and all hooked into the same thing. So we're able to do our controlled releases of gases, and all the instruments will see the same material almost simultaneously. So we're going to start the detection. Unfortunately, AP4C, which has gone off, which will go off the fastest, is a little bit hard to see. It'll be on the second channel on the HN. So you are getting some hits on the MSA meter. That's because of the hydrogen that's present in the solution, but the release was done, and the AP4C is able to detect it within 11 seconds. Then your PID, which is your second fastest responding, will see it after about 16 seconds. The Explore IR starts to see it. It's going to take it a while to actually identify what it is, but it starts to see it after 20 seconds. And then, so all of your PIDs are basically going off fairly similar to each other. And then you'll see in just a little bit that your IMS instrument is going to start going off with it. So each instrument kind of has sensitivity to a different level or different degree. As a general rule, detectors, as you get down to lower and lower concentrations, take a little bit longer for you to see it. At a higher concentration, they can see them faster. But again, if you're using certain instruments to validate, so this is one of the reasons why we don't really recommend using IMS as a post-decon evaluation, just because of its response time and sensitivity associated with it. But they are able to see, in this case, it's something that's, all detectors are able to see. It's pretty low vapor pressure. So the vapor pressure is such that makes it pretty easy to detect in vapor form for a lot of these materials. It is a common material that we see, but you just have to understand your detector response time. So if you're using a detector that's going to take 40 seconds to see something, just be aware of it. It's not that it's bad, but if you're trying to make a decision after 5 seconds and you're impatient, then it's taking a while to do that. And then the Explorer IR is actually identifying that material. In the case of the IMS instrument, it's not able to identify what it is at that concentration. So we're right around 50 parts per million that we've introduced into the solution. But it is able to detect that something's there, just not telling you what associated it is. In the case of the other materials, in the case of AP4C, it's telling you what class of materials, so it's telling you hydrogen nitrogen bonds are present. In the case of the PIDs, it should be able to identify those depending on what you have in the solution, or it'll be cross-sensitive to other materials. But that's a really good video just to show same concentration to multiple detectors simultaneously, and the different capabilities that associate with them as far as both response time and identification.
And Scott, it's important to note also that part of the response time is I started this right when we released the ammonia. And so the ammonia had to travel down through all of the tubing from the tank and then into the mixing sensor. So reality is you would take about 10 seconds off of all of these. So you would have about 1 second for the AP4C, about 5 seconds for the PIDs. Reality is you have about 10 seconds the Explore IR detected it, and about 30 seconds the ChemPro detected it. Now, because this is at 50 parts per million, it was just above the identification threshold for the Explore IR, but just below the identification threshold for the ChemPro. So if we had increased the concentration or doubled it to about 100 parts per million, it would have all gone faster, but also the ChemPro would also have identified it. And so that was all about concentrations and time profiles. So to bring us back around, I just wanted to bring forward, and these couple of slides are from First Line, but what are we getting by modernizing our decon system? We're reducing the spread of contaminants, we're minimizing all the logistics requirements, and we're greatly reducing the footprint for decon. If you could just look to the right-hand side here, where we have a preliminary gross decon type of system for emergency decon, right outside the area where the contamination event occurred. Therefore, we do not drag all the contaminants throughout the building. Same thing here is where we're greatly reducing the total amount of waste. By minimizing the use of water in a lot of our decon processes, we are greatly reducing time on target and greatly reducing the waste. And in fact, in many cases, we're greatly reducing the total contamination load to the person, because we do have a wash-in effect that happens with a lot of water use, and we were actually causing more permeation than was necessary for a lot of our operators. With that said, we strongly believe that detection and decon needs to be treated as a system. We need to detect that a contamination event occurred, then we need to decontaminate that specifically to what we saw, and then we need to detect at the end to validate that the system is complete. The decon approach has to get driven by the material, its state, the chemistry involved, the vapor density, all of those things that you saw in the videos. Also, please choose your decon location wisely. We want to minimize the exposure to the person performing the decon, but we also need to make sure we have our best chance at measuring if there is any contamination remaining. The detector sensitivity and response time are critical to this type of event. While all of those detectors might be good pre-decon, not all of them are good post-decon. In the post-decon phase, we need to be measuring in the parts per billion range, not the parts per million range. We need to get down below the occupational exposure standards, not be between the occupational exposure standards in IDLH. And so that starts changing what we use pre-decon and post-decon. And just remember, just because an individual has gone through a decon line, it doesn't guarantee that they're clean or safe. And frankly, if we thought somebody needed to go through a decon line, they also need to go through and do follow-up cleaning. With that, I did want to take a moment to thank a couple of different people. First Line Technology, even though there was a major snow event in Fredericksburg when we were there, they did open up Ben Hershko would allow us to use their vent hoods regardless. It's from environmental game and helped us do. And then of course the Safe Wear Hazard 3 team for allowing us to use a couple of the different charts that we used in the presentation because they're easy to use guidance documents for you as first responders. Yeah, I'm just going to check and see if there's other questions on here. Don't see any others. I was trying to answer them as we went through. So if you do have more questions, please feel free to contact Scott or I at our emails or our cell phone numbers on the screen. We will be downloading this presentation, this video, and saving it. And then you'll receive an email follow-up with how to gain access to that video of this entire presentation. We don't send out the actual presentation materials, but we do send out the video so that it's taken in context. With that, Scott, do you have any final comments?
No, I don't. Yeah, just definitely if there's any questions, please feel free to reach out. Hopefully it was pretty self-explanatory, but we might have missed something here or there or didn't do a good job of explaining something. So we're here to.
One of the things that I also brought up, I didn't think of is the thanks, Ansley. Ansley's calling from Singapore, so he's at like 1 in the morning right now. So one of the things that we saw in there was the hydrogen flame. And this is one that I brought up to the ProEngine team is I always thought that it was a high pressure hydrogen cylinder. And in reality, it's not. There is no high pressure cylinder involved in the AP4C operations. The cylinder that's used for the hydrogen is just absorbing hydrogen onto a physical absorbent material, really. And so what's happening is that having the metal cylinder like that allows for equal heating across the surface to release the absorbed hydrogen. I completely had that all wrong for years. So thank you to the AP4C team and the ProEngine team for bringing that to my attention as I was trying to get rid of high pressure cylinders that had no pressure in them. And then the other one is, I know we showed you that little headspace sampler, and the brains behind that, Olivier, is online with us today. So Olivier, thank you for taking our ideas and making it an actual capability. And hopefully we'll get that out to more people soon. With that, thank you everybody. Stay safe out there, and please continue to tune in for our ProEngine Academy courses. Have a good day.
Thanks.